Every Friday on the Context Engineers Discord, we bring CTOs, AI researchers, and engineers who come and present their work. This week, we're extremely fortunate to have two amazing speakers. We also have Maria Benavente, who's going to talk about different architectures behind memory layers for AI agents. Enjoy. Maria is going to talk about memory for agents. So pretty excited about this. Thanks so much, Maria, for presenting today. And again, towards the end, if anyone wants to do a lightning talk, feel free to. I'll let you, Maria, introduce yourself and present your topic.
Yeah, no, thanks for the opportunity. I'm super excited about this. I also like presenting after this amazing work that we just saw. It's very cool as well. Let me share my screen. So yeah, with the content I'm presenting today, it's called Engineering the Illusion of Memory in Stateless Systems. Before I start, a little bit about myself. My name is Maria. Used to work at Apple, and right now I'm taking some time to re-explore kind of like technical interests. So I'm just spending most of my days like reading papers, like writing code to like tinker like some ideas. My main areas of interest right now is like LLM memories and context engineering, data, a little bit of everything. I'm really taking this time to explore, to find what I want to do next. So if anyone in the audience also has some ideas of like some cool things to work on, the content that I put together today is like an overview analysis that I made of like the current LLM memory field. LLMs are stateless systems. So if we expect them to have like a stateful behavior, we need to like build the illusion of them having like a memory. So the first question here is, what do we actually mean by a memory? So let's break that down. The concept of memory has like different categories. There is not a ground truth here, but I think that the taxonomy that I'm presenting is the standard in the field. First, we have parametric memory. This one is the frozen knowledge inside of the weights of the model. So it's the one that is like learned during training. The only way to update it is like changing the model. It's like changing the parameters. So we would need to like retrain or fine tune it. The next one is contextual memory or short-term memory, which is the information given to the model within. It is limited to a context window. It has close to perfect recall, although the quality like degrades. Context grows, and it also gets like, it can get like potentially polluted. And then we need to take into account as well that inference cost grows quite drastically. Yeah. Well, to recap quickly on this, we have like the parametric memory, so like the frozen knowledge in the model. Then the contextual memory, which it's like what the model has like in memory to work with memory like in the context window. Then we also have like extended memory and long-term memory. Bring them together to the slide because there is like a bit of overlap on like between these two concepts. So how I like to think about it is like extended memory is what most of us would have as like RAG in our minds. And then long-term memory, it's closer to like functional or like working memory, or closer to like human-like memory. A good analogy for this is that extended memory could be kind of like the equivalent of like accessing a library. And then long-term memory, it's more like accessing your personal notebook and like or personalized information that you have. Any question or complain about the taxonomy before we continue?
Yeah, I have a question about long-term memory. How is that even implemented? Because I assume it needs to be added to the context, right? So every time, with every...
Yeah, in the same way that, so that's why I separated a bit the first two and the second two. So in the same way that parametric memory, it's always there because it's like all encapsulated in the weights. Then contextual memory is kind of like what we add on runtime, so to say. So both extended memory and long-term memory, what they both do is like donate context to the contextual memory, in the sense that the extended memory and the long-term memory are like working like in parallel, so to say, like next to the LLM, and then they feed the contextual memory of the LLM with data.
Oh, okay.
Does
makes
that
sense.
make sense?
Yeah, it makes sense. Thank you.
Okay, if we don't have other question, I'll continue with their framing that I wanted to share an intro to the architectures. This is what I called the blueprint of adaptive memory. It's essentially like a wish list of requirements that a truly like adaptable and agentic memory system should, according to myself. I haven't done a lot of like research on this area. It's just like what I have in mind of like how these systems should operate. So these systems like should not yet store data. Like gonna be mostly focusing here is like around the long-term memory. So not like how we handle a lot of information um, in a library, but more like how do we keep like the memory for the agents, personalized agent and agent memory. So these systems shouldn't just like store data, but they should like evolve with it. So I see like 4 pillars of like this adaptable and agentic memory desired system. First one is like temporal adaptation. So we need to treat the memory of the agent as a living memory. So in a traditional database, data is there until you delete it. But that's not the case with humans. Like with humans, like we adapt our memories and our data with time. So we need to be like an adaptive system that it kind of like naturally decays on information, adds new ones, etc., or like updates as well. And something that were like relevant a year ago may not be relevant anymore, or they even may be false. So we need to like implement it. The other like must have is like sustainable growth. This is like a self-maintenance. We need a self-maintenance mechanism. It's like like in for humans, it's true that we always have like space for knowledge, and in many cases, it's also because we like leave space for this. I like to think about like the movie like In and Out, when they like overnight kind of like delete old memories. So I think that's a base for like a baseline for sustainable growth, and we need agentic systems that do the same with their. They should be context aware. So, data and language really shift meaning according to the context. So an adaptive memory system needs to like learn what is like important for the context and what not. So it's important that it like filters out noise so that the operating agent get only the relevant memory. And last but not least, we have like granularity and navigation, which is probably my favorite, which like we rarely need memory in just like that one abstraction. Like sometimes I want to remember that you went on a vacation, and sometimes I want to remember, I don't know, like all of the plans that you told me about that vacation, or like the restaurants that you went in. So like when you being like a data point, it can like expand a lot in terms of like much you like information from it. So I think that an agent that is really good with memory should be able to understand that granularity and be able to navigate it very well. So to recap, like the wish list for an agentic memory would be like temporal adaptation, uh, sustainable growth, context awareness, and granularity and navigation. Like using this framing for me, it really helped me like the capabilities of the memory systems that I will present now. So yeah, I hope it helps. And the last intro slide, I will be presenting like the 4 selected architectures for today. The first one is MemZero, which is the go-to memory. They present themselves as the go-to memory for a layer 4 applications. They are very developer friendly, and they offer solutions to like every kind of like memory problem. So like no matter if you are like looking more for a RAG or for a temporal system, they try to be like a all in one. So in a similar space, like very production ready, developer friendly, we have ZEPP, which specializes in temporal reasoning. So they rely on like a temporal graph named Graffiti that helps the system like support like reasoning about temporal changes, which is also very, very interesting. So these two, yeah, are like production ready, they're easy to plug and play, and they're like mostly focused on commercial applications. There is right now an open discussion around the metrics to compare the performance of these two systems. There is like an open debate on which one works better for like some of the use cases. I don't want to position myself on that debate, so I'm not going to present kind of like any metrics, or I'm not going to comment on which one works better at all. And also, like, I wanted my presentation today like to be focused on the logic and like the interesting ideas behind each of the architectures, instead of being like a deep dive in all of the paper. So I'm just going to be covering like the logic behind each of these approaches. Okay, so these two are like the more like production ready systems in terms of like they have, developer friendly, open API, etc. Then I'm going to present other two that I really like because of like the novel ideas behind the architecture. The first one is MemGPT by a company named Lida. They is like based on this LLM as an operating system vision. They treat memory as the memory of the OS, like similar to computers having like static, like the disk storage and the RAM, and it like manages that. What MemGPT does is like they try to do the same, and they create like a virtual context, and with tools they swap the content that is there. This is probably not making sense right now. Just like keep in mind that their goal is to simulate infinite memory. The last one I want to cover is AEMEM, which is a agentic memory architecture that aims to self-organize. It is inspired on a note-taking technique from the 70s. It aims to like autonomously let the system to like create, link, and evolve the information. Yeah, these are like the four architectures that I wanted to like. Great. So MemZero, they presented this on a paper named MemZero: Building Production-Ready AI Agents with a Scalable Long-Term Memory. And looking under the hood, MemZero is just like, it's not just one thing. They actually present two different architectures. The first one is like a vector-based approach. And they call this one like MemZero. And it's great for kind of like efficient, high-speed retrieval because it's like the classic semantic search. And then in this paper, they also introduced another one called MemZero-G, which is a graph-based approach that is designed to capture more complex relationship between data points that the vectors that only work with the semantics sometimes. These two systems, they both operate on a logic of like two phases, where the first phase is a phase, where the system parses information to pull out the kind of like the interesting information, like the facts, preference, and memories from the text. And then they have like an update phase, where the system asynchronously writes those insights back into the storage, ensuring that the memory evolves, but without slowing the user experience. I like to think of this update phase something like similar to like how our brain operates at night, right? Like we have everything, all of that, like in the in the memory for the day, and then we'll go to sleep, and then like our brain kind of like rearranges the information that we learned during the day, and then the next morning we are like a bit changed with the new knowledge. So with this high level overview of like the kind of like the MemZero ecosystem with like two architectures and each of them having two phases, I'm gonna present the logic behind each of these architectures. For MemZero, like the one that is like vector based, like the most interesting part, the most interesting thing they do here is that they have several filters to try to keep the memory clean and as less noisy as possible. So first, in the extraction phase, in the purple box, the system constructs like a hybrid context, like a hybrid, like in the context window, it constructs like content for there, using the compressed summary of all of the memories plus the recent messages. So this is a great example of like the question that I got earlier in the presentation about what was the difference between the context window and the memories, etc. This is a great example of, we have a database with stored knowledge, and then the way that we feed the LLM with that is like we take some of the information, or only the one that we think is relevant, and then we like append it to the context window. So it's like a way to feed data to the LLM without overflowing the context window. Like the fact that it like adds this global summary plus local context is very interesting, because it's like a very good balance between like general information, recent information, etc. Then we have an update phase in green to the right, and it also like added some smart logic to try to perform better than how standard RAGs do. How this works asynchronously is that once that a fact is extracted, the system searches for similar existing memories in the LLM, then uses one of these available options that it has through tools. Like it can like it. So like you get a new memory, and then instead of just like throw it into the database, it first checks if there's like something similar to it. And then for each of those memories that are similar, it can like decide to do one of the following 4 options, which are the new memory, update one of the memories, delete one of the memories, or no operation if there is like to change. So this logic basically prevents the database from filling up with duplicates or contradictions. I think that mainly like those two. So this is how like data ingestion works. And then on the retrieval phase, the system like utilizes like dense vector retrieval of like semantic search on the database to see what might be relevant. So it's very similar to like a RAG, but like using highly curated zero-G. So this one is like the graph-based architecture. So it is designed for when relationships matter more than keywords. In the extraction phase, like the LLM does not just pull out a sentence, but it like also use like first extracts entities and then generates links among them. So it's like we first identify the nouns, so like people, places, concepts, events, and then there is a second LLM, the generator, like the relation generator, specifies how they connect. So for example, the first LLM would like identify like Alice and San Francisco. And then the second LLM in between the connection between them, which would be lives in. So then the result of the extraction phase are like this set of triplets. Then the triplets are like Alice lives in San Francisco. And with that, we go into the update phase, which is like how we ingest those triplets into the graph. So we do that through like a conflict detector and update resolver architecture. So when a new triplet arrives, instead of just like placing it into the graph, what it does is like first see if there is like a conflict with any of the existing triplets. And if not, it's just like ingested. And if there is a conflict, it triggers like this update conflict resolver where it like figures out data needs to like be updated for this. That's how like ingestion works. And then for retrieval, it also uses like some sophisticated dual strategy. It's like the system can either like walk the graph by specific entities, and it also can perform semantic search with the triplets directly. So it does both, right? It looks for nodes that are potentially interesting, then performs and hops. On parallel of that, it also performs like direct semantic search on triplets to find coincidences in like full meaning of the triplets. So this allows like the agent to like navigate pretty complex data and like interconnected facts. Like simple vector search probably wouldn't work that well here. So comparing the two, just to like summarize like the MemZero ecosystem. MemZero, the standard one, is like the default. So it's built for like speed and efficiency. It stores the data just like as unstructured vectors. The token cost is low. The retrieval speed is fast. So it's very good for like simple hop queries. But for example, if you have a temporal, if there is like temporal complexity involved, then MEM0G would adapt better to that use case. So if your application is to like understand relationships each over time, like, I don't know, like the user's life where people like, I don't know, move cities, change jobs, change partners. So like then MEM0G may be like a better use case for you. Questions about MEM0 before we move into ZEPP? So a second architecture today, it's called ZEPP. It was presented in a paper named Temporal Knowledge Graph Architecture for Agent Memories. And this system is a memory system built around graffiti, which is a dynamic, temporally aware knowledge graph. Yeah, think of a knowledge graph where you like also have this idea of inside of it. I will explain later how this translates into like an architecture. It is designed to like understand facts that change over time, so similar to MEM0G. Instead of searching in a blob of documents, it like uses graphs to interconnect the information. This one is best suited for like use cases where agents need to answer multi-hop questions, perform temporal complex reasoning, or like synthesize information across like long and evolving setup. Yeah, as a personal assistant, for example, who need to understand someone's life. In order to explain the architecture, I think that it's important to first understand how it does so through three different subgraphs. The first one is this is the bottom layer that stores the raw data. So every message exactly as it happened, just like it gets in, it gets stored in the episode sub. Then we have like the semantic entity subgraph, which is the most important one here. This is where the system extracts, which are formed by like identified entities, so people, places, events, and the relationships between them. So they are similar to the triplets that we just saw with MEM0G, but then these facts, they are richer in context, basically because they capture also natural language, they capture a structured relationship, and they capture as well temporal metadata. Here's an example of how this looks. So we would have, for example, if I say that I quit my job at Apple last month, then it would like store the fact. So the user quit their job at Apple. And then it would store like this triplet. So source entity user, target entity Apple, and then relationship type is quit job at. And also facts normally have temporal fields, but I will explain this later because I think it's going to be easier to understand. So just keep in mind that it has like natural language, it has like relationships similar to the triplets as zero, and it also has. And the last graph here is the community graph. I like to think about this one as like, think of the semantic entity subgraph and then visualize it. So visualize like the graph floating into space. And then you create clusters of those nodes. And then you summarize each of the clusters. So basically, the community node, the community like graphs is like one where each of the nodes represent that group of semantic entities. So it's like great for abstraction and navigation. So I think that this slide is like a great example of what I was explaining at the beginning of like granularity and navigation. Yeah, because it presents the system with like different levels of the same data. Okay, we'll go into the next slide where I'll explain why the semantic entity subgraph is the most important one. And also I'll introduce how the temporal data looks like.